you ask someone to describe Earth from space, they'll probably say the same thing we all learned as kids. It's the blue planet. More than 70% of Earth's surface is covered by water. Oceans stretch from horizon to horizon. Clouds move enormous amounts of moisture around the globe. From a distance, water seems almost limitless. But appearances can be deceiving, because despite all that blue, the amount of fresh water available to support nearly 8 billion people is surprisingly small. Of the small amount that is fresh water, most of it's locked away as glaciers, snowpack, or underground. And that means many freshwater systems that we depend on aren't really reservoirs at all. They're storage systems, natural savings accounts that collect water during colder, wetter periods and release it when we need it most. Today, we're going to explore where Earth's freshwater actually comes from, why glaciers are far more important than people realize, and what happens when some of our planet's largest natural water storage systems begin to change. Welcome back to the podcast. I'm Dr. Mack, and this is The Climate Translation. When I teach introductory Earth science, I often start with a simple question. How much of Earth's water do you think that humans can actually use? The answers are usually all over the place, from 20%, 30%, sometimes half. Honestly, I understand why. If you ever looked at a globe, the water seems everywhere. Oceans dominate the map. Lakes and rivers crisscross the continents. Satellite images show clouds constantly moving moisture around the atmosphere. The water here feels abundant. But once you start doing the math, the picture changes quickly. About 97% of all the water on Earth is salt water, contained in our oceans. That leaves only about 3% or less as fresh water. Now, 3% of all the water on Earth is still a lot of water. It sounds encouraging, but we still have to keep going, because most of that fresh water isn't available to us either. Nearly 70% of that 3% is locked away in glaciers and ice sheets, and another large portion exists as groundwater deep below the surface, often difficult to access. That leaves only a tiny fraction in places we normally think about when we hear the word freshwater: rivers, lakes, wetlands, and reservoirs. The water we rely on every day is actually one of the smallest slices of the entire global water budget on this planet. I think one reason people find this surprising is because we tend to focus on where water is visible. You can see rivers and lakes and reservoirs, but those are really just kind of like the checking account of the global water system. Much of the water is stored somewhere else, and that's where glaciers become important. When people hear the word glacier, they think of remote places like Greenland, Antarctica, and high mountain peaks far away from where people live. But glaciers are much more than just giant blocks of ice. They are storage systems. In some ways, they're nature's version of a savings account. Every winter, snow accumulates in high mountain regions. If enough snow survives the summer melt season, it gradually is compacted into ice. Over years, decades, centuries, even millennia, glaciers store water that originally fell as precipitation. What makes glaciers remarkable is that they store not just water, but time. Think about that a moment. A snowflake that falls in the mountains today may not become river water for years, decades, centuries. The glacier acts like a delayed delivery system, slowly releasing water long after it originally fell from the sky. And that delayed release has consequences, because rivers don't need the most water during the wet season. They need it during the dry season, when rainfall is limited and temperatures are highest, when crops are growing and cities need the most water. Glaciers help bridge that gap. They collect water during cold periods and release it during the warm periods. And for thousands of years, many of the world's major river systems have depended on that natural storage cycle. So, what happens when nature's savings account starts to shrink? At this point, it might be tempting to think that some of the melting glaciers we see these days, due to climate change, could actually solve some water shortages. After all, if ice is turning into liquid water, shouldn't rivers be swelling and getting more water? And in the short term, that's exactly what happens. This is where things become counterintuitive to people who don't really understand the science. Imagine you have a retirement account. Under normal circumstances, you might live off the interest it generates. The account remains stable as long as you're only spending what it earns in interest. Now, imagine you start withdrawing some of the principal as well. At first, life would be great. You have more money than before and you can spend more freely. But of course, there's a problem. Your larger withdrawals are only possible because the account itself is getting smaller. Glaciers behave in a similar way. When a glacier loses mass, more water enters the nearby river, and for a period of time, even a couple of years, stream flow can actually increase. Communities downstream might see more water available during warm seasons, and reservoirs might receive larger inflows. The system might appear healthy for a while, even as the glacier itself is shrinking. Scientists refer to this period as increased runoff. But eventually, something important happens. The glacier itself is getting smaller, and the smaller glacier contains less ice available to melt. At some point, the system reaches what hydrologists call peak water. Peak water is the moment when meltwater production reaches its maximum. After that point, the trend reverses. The glacier continues melting, but because there's less ice, annual runoff begins to decline year after year. It's like cutting down a forest. The first few years you might have a lot of lumber, but eventually there's fewer trees left to harvest. The same principle applies to stored ice. And researchers are increasingly observing this pattern in mountain regions across the world. Some glacier-fed watersheds have already passed peak water. Others are expected to reach it during this century. The timing varies from place to place because every glacier is different. Some are large and some are small. Some exist in very cold climates and others are experiencing rapid retreat. But the underlying physics remains the same. You can only withdraw stored water for so long before that savings account begins to run low. Now, our glaciers aren't disappearing everywhere overnight, and many river systems receive water from multiple sources, including rainfall and seasonal snowpack and groundwater sources. But the trend is significant because glaciers have historically provided something extremely valuable: reliability. They act as a buffer. When a dry year occurs, glaciers continue to melt. When precipitation is lower than normal, glaciers still release water into rivers. They help smooth the natural ups and downs of the hydrologic cycle. As those frozen reserves become smaller, the buffering capacity begins to weaken. And this isn't just happening in one part of the world. It's occurring across mountain ranges on every continent. Which means the question is no longer whether glacier loss affects freshwater resources. The question is how many people depend on those frozen reserves. And the answer turns out to be a lot more than you might realize. Glaciers don't exist in isolation. They sit at the headwaters of some of the most important river systems on Earth. In fact, many of the world's major rivers began as snow and ice in high mountain source regions. If you travel to South Asia, you find the Himalayas, sometimes called the Third Pole because of the enormous mass of ice stored there. These mountains feed river systems like the Indus, the Ganges, and the Brahmaputra. Together, these rivers support millions of people through agriculture, transportation, industry, and drinking water supplies. If you move west into Europe, you find the Alps. The glaciers there feed rivers such as the Rhine, the Rhone, and the Po. Rivers there have shaped trade routes, agriculture, and human settlement for centuries. In South America, the Andes become the story. Communities from Colombia to Chile depend on the seasonal meltwater from the mountain glaciers, particularly during the dry season when rainfall becomes scarce. And in North America, the Rocky Mountains serve a similar role. Snowpack and glacier-fed watersheds help supply water to major river systems that support cities, the agriculture, recreation, and energy production across much of the United States and Canada. These are all different continents and climates, different cultures, but they all have the same basic physics. Water falls from the atmosphere, it becomes stored as snow and ice, and that stored water is gradually released over time. For generations, we've treated these frozen reservoirs like a permanent feature of the landscape. They were simply there, reliable and predictable, and part of the background. But scientists are observing these systems are changing. One of the reasons glaciers receive so much scientific attention and news attention is because they respond directly to long-term shifts in temperature. Glaciers gain mass when snowfall exceeds melting, and they lose mass when melting exceeds snowfall. And when researchers begin comparing observations around the world, clear patterns have emerged. Many glaciers are shrinking. Not all, and not all at the same rate, but enough of them that a global trend is unmistakable. In fact, recent monitoring efforts have documented some of the largest glacier loss ever recorded. Scientists tracking mountain glaciers worldwide have found that the past decade has contained many of the most significant ice loss years in the observable record. Now, it's important to understand what all of this means. When scientists talk about glaciers losing hundreds of billions of tons of ice, they're not suggesting that every glacier on the planet is going to disappear. Nor are they suggesting that every community dependent on glacier melt is going to face an immediate crisis. But what we are observing is a long-term reduction in the overall storage. If we think back to our savings account analogy, the concern isn't the account is going to be zero and close tomorrow. It's that the withdrawals have consistently exceeded the deposits, and year after year, decade after decade, the amounts have decreased. Eventually, the trend changes what the account can provide. And that's why glacier loss has become such an important climate indicator. Glaciers integrate years of weather into a single signal. A hot summer might cause additional melting. A snowy winter might temporarily slow it down. But over long periods of time, glaciers have revealed whether the balance is changing. And increasingly, the balance appears to be shifting towards loss. What makes this especially important is that glacier loss is not occurring by itself. Many of the same regions experiencing shrinking glaciers are also facing growing populations, increasing water demand, expanding agriculture, and in some cases, reoccurring severe drought. In other words, our storage system, our savings account of the planet, is changing at the same time human demand is continuing to grow exponentially. And that combination brings us back to one of the best examples of how these forces can interact, the American West. One of the things I've learned after years of teaching meteorology and climate science is that water problems are not always about how much water exists. Sometimes they're about when the water arrives. Imagine your employer suddenly decided to pay your salary in 2 large checks in April and October, instead of spreading it across 12 months. The total amount of money is still the same, but managing your finances might be more difficult. You still have bills in February and November, and you still need money throughout the year. It means you have to budget a lot more carefully. Water systems work in a surprisingly similar way. For centuries, snowpack and glaciers have helped regulate the timing of our water delivery. Winter storms deposit snow in the mountains. Some of that snow melts during the spring runoff. Some become stored as glacier ice and released more gradually over time. The result is a relatively steady flow of water into our rivers and reservoirs. Nature, in a sense, is spreading out the payments. But as mountain ice declines and snowpack becomes less reliable in regions, the timing has begun to shift. More precipitation may arrive as rain instead of snow. More runoff may occur earlier in the year. Less water may remain available during the hottest months when the demand is highest. It creates a challenge for systems that were designed around older, more reliable patterns. The Colorado River Basin is a great example. When most people think about the river, they picture the canyons and the deserts. But the river itself began hundreds of miles away in the mountains. Historically, winter snow accumulated in the Rockies and then melted gradually through the spring and summer. Reservoirs such as Lake Powell and Lake Mead were built and designed around that seasonal cycle. The challenge facing water managers today is the cycle is not behaving the way it once did. Warmer temperatures have reduced the snowpack, and earlier snowmelt has changed when water enters the system. Droughts now reduce how much of that water ultimately reaches reservoirs. And all of this is happening at the same time that millions of people have moved to the Southwest. Large agricultural regions have sprung up, and growing cities such as Las Vegas continue to depend on the river. The issue isn't simply that there's less water. It's that the storage and delivery system is becoming less predictable. And similar conversations are happening around the world. Communities in the Andes are asking how to manage water supplies as their tropical glaciers retreat. Countries dependent on the Himalayan river systems are studying how future changes in snow and ice might affect their water availability. And European nations are evaluating how shrinking alpine glaciers will influence river flow, agriculture, and their hydropower production. These are all different locations and climates, but they're all asking the same question. How much water can we store? When will it arrive? And how reliable will it be in the future? One thing I think that's important to remember is that glaciers have never been the only source of fresh water. Our rainfall still matters. Our groundwater still matters. The snowpack and human management matters. The future of fresh water isn't determined by glaciers alone. But glaciers have long served as nature's most effective buffering systems. They smooth out the dry years and sustain rivers during hot summers. They have provided a reserve that could be drawn upon when conditions became difficult. As the frozen reserves become smaller, some of the natural buffering capacity has begun to weaken, and that means the timing, storage, and management of water has become more important than it was before. Ultimately, the challenge isn't simply having water. It's having water available when and where people need it. Our blue marble, the ocean planet Earth, has abundant water, but the reality is that the available fresh water is a much more finite resource. The water exists within a small and more delicate system of rivers, lakes, groundwater, snowpack, and glaciers. For thousands of years, many of those systems operated within a fairly predictable rhythm. Water fell as snow, accumulated in the mountains, and was gradually released as the seasons changed. As climate change alters weather patterns and climate zones, glaciers, the savings accounts for most of our available fresh water, are beginning to shrink. Our rivers and lakes won't disappear overnight, but the timing, storage, and distribution of the water that feeds them is changing. And as those patterns change, society will have to adapt right alongside them. We need to take note of the change we're seeing around us, consider our response to that change, and plan for a future that may be very different than our past. I'm Dr. Mack, and this has been The Climate Translation. If you have a question about the climate that you've been too afraid to ask, or if you have a differing opinion, I want to hear from you. I can use your viewpoint in a future episode. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.